Okay, so today we're going over electron configurations. Now, electron configurations are basically like the address of the electron. So I'll kind of show you guys what that means a little bit later on. But imagine you were visiting like a friend or a friend was coming to visit you into town. They would basically need a variety of information to find out where you are, especially if you live like in an apartment building. So they would need to know the address of your building. They would need to know what floor you live on, maybe like which side of the hallway you are in, if you share your, I guess, room with like multiple people or your apartment with multiple people, maybe what room you would live in, especially if you live in like a college dorm. So there's a lot of different pieces of information that your friend would need to locate where you are. And in the same way, electrons basically have a bunch of different information that you can use to locate where they are. So we kind of went over this in the beginning. This part should be review. There's valence electrons, which are on the outermost shell, right? And then your core electrons are all the other electrons that are kind of before the valence electron shell. And even in the core electron layers, you can either be in energy level 1, which is closest to the nucleus, or energy level 2, etc. So there's a bunch of different information that you can use to figure out where the electron is. Now, I'm going to have you guys look at the periodic table. And why don't you guys, let me launch the poll and then I'll take attendance while you guys do that. So answer these questions that are right here and let me launch the poll. Okay, so this should have all been reviewed. So first of all, how many total electrons does silicon have? So if you look here, right, silicon has an atomic number of 14. So since it's a neutral atom right now, it would have 14 electrons as well. How many valence electrons does it have? So again, just look at the column number. So it's in column 14. And if you look at the last digit, that means it has 4 valence electrons. And then how many core electrons does silicon have? So the core electrons are basically any electron that's not a valence electron. So you would just subtract 4 from 14. So that means it would have 10 core electrons. And then which has a higher energy level, silicon or carbon? So remember, the period number tells you what energy level or what's the highest energy level of that element. So silicon, the highest energy level that it has is 3. So silicon would have a greater energy level than carbon, which only has the highest energy level of 2. Okay, so let's get into electron configurations. Now, an electron's address has 3 main parts: energy level, sublevel, and orbital. And these are kind of similar, but we'll talk about the difference between these two in our next lesson. And there's actually 4 different parts for an electron's quote unquote address. But we're only going to be talking about like the electron configuration today. So I'm just going to give you guys a heads up. This part is pretty confusing or very conceptual. And don't worry so much if you don't understand this part yet. When we get into like our later lessons that I cover, then it'll make a little bit more sense. But for today, I'm just going to give you kind of like an intro to it. But again, don't worry too much about understanding this completely. The main thing that you need to get out of today is knowing how to write electron configurations. So if you can do the examples, then you're pretty good for today. But I'm still going to talk about exactly, or at least give you an intro to what these mean. But again, don't worry so much about it for today. You'll kind of get a better idea as we go through the later lessons. But I need you to learn how to write electron configurations today. Okay, so the electron configuration is basically going to tell you different things about the electron and you can use that information to figure out where the electron is and what it's doing inside of the atom. So if you look, the address, quote unquote, of an electron, it's going to, or the electron configuration, it's going to talk about the energy level of the electron, the sublevel of the electrons, and then the number of electrons that you have in that sublevel. So first of all, what the heck is a sublevel? So if you remember, if we draw a Bohr model for an atom, right? So let's say I just draw a random atom. It kind of, and then here inside is the nucleus. It's similar to planets orbiting the sun, right? We always picture it as electrons are moving in a circle around the nucleus, like the planets orbiting in an ellipse around the sun. But this is a very like two-dimensional picture of what's going on. Electrons actually move in different types of shapes. So they don't all just move in a circle. So these shapes right here, you have S, P, D, and F. And these are the different names of the shapes that electrons can kind of move in, or the path of the electrons. So if you have an electron in the S sublevel, it's going to move in like this little sphere direction. So you'll have an electron that'll just move in like a sphere. But again, it's 3D, so it'll like actually move through the z-axis as well. And then if you have an electron that's in the P sublevel, it'll move in like this, I guess, dumbbell-looking shape. And then if you have an electron in the D sublevel, it'll move in this wet pattern. And then F sublevel moves in like this crazy-looking flower pattern. Okay, so again, the sublevels basically describe the shape of the electron's movement. So using the electron configuration, you can figure out what energy level the electron is and the shape of the electron's movement. So here we have hydrogen, and if I draw the Bohr model for hydrogen, right, you can see it just has one electron. So this electron is hydrogen's electron, and this is the electron configuration. Now I'm going to go over like how to write the electron configuration, but before we do that, I'm just going to explain again. So this big number right here, that's your energy level. And you can see here, right, it's an energy level 1. So this electron is an energy level 1. The sublevel describes, again, the shape of the electron's movement. So this electron right here, even though we draw it like two-dimensionally here, it's actually, if we look at it in real life, it's traveling in this sphere shape. And then the number of electrons, so it tells you here, you only have one electron. If we draw the Bohr model for helium, right, you could see here, this would be 1s2. So again, energy level 1, both of these electrons are at energy level 1. They're both in the S sublevel, so they both move in like a sphere-shaped pattern. And then it tells you the number of electrons that you have, so 2, which is 2 electrons here. So the exponent is always your number of electrons. Okay, so let's go over how the heck you write electron configurations for atoms. So what you need to do is you need to either click this link here or just open it up from Canvas like I had linked right here. So I'm going to kind of split my screen so you can kind of see both of them. Sorry, this is the wrong one right here. So we're going to be mainly using this today. Okay, and in case, like if we were in the actual classroom, I would have you guys memorize this, but obviously since we're doing distance, you guys can just use this. Okay, so basically what you're going to do is you're just going to follow whatever element that you have. You're going to start from the beginning and you're just going to follow this chart in order until you reach your desired element. So you always start at hydrogen and you just follow the table in terms of atomic number until you reach the element that you want. So for example, set 1, right? The first question is we're doing lithium, which is right here. So let's start at hydrogen and just follow the table until we reach lithium. So hydrogen is 1s, right? And in the 1s sublevel, we just count how many electrons we have. So we have 1 electron, 2 electrons. So I would write 1s and then put an exponent of 2. And then now I move on to the next sublevel. So here, now I'm at 2s. And lithium stops right here. So this would be 2s1. And that would pretty much be it. So the lithium's electron configuration would be 1s2. So 1s2, 2s1. And then let me just draw the Bohr model so you can kind of see what that means. So again, lithium has 2 electrons in the first energy level, another electron in the second energy level. So then these 2 electrons here, these would be my 1s2 electrons, right? So energy level 1, they both move in like a sphere-shaped pattern. And then my next electron, this would be my 2s1 electron. And you can see, right, this electron here is in energy level 2, and it also moves in a sphere-shaped pattern. So that would be for lithium. Okay, so let me do sulfur, and then I'm going to have you guys practice these ones on your own. So for sulfur, hold on, give me a second. Okay, so for sulfur, sulfur is right here. So again, I'm going to start from the beginning. So I have 1s, 1s1, 1s2. So my 1s sublevel is filled. And then moving on, I have 2s. So this would be 2s1, 2s2. And then keep moving. Whoops. Here, now I'm at 2p. So I would have 2p. And then count how many electrons you have. So 2p, 1, 2, 3, 4, 5, 6. So this sublevel is filled. So I would go 2p6. And then moving on, I am right here now. So this is 3s. And then this sublevel is also filled. So this would be 3s1, 3s2. And then finally, we're almost there at sulfur. So right here. So now we're at 3p. And then just count how many electrons you have until you reach sulfur. You would have 3p, 1, 2, 3, 4. So 3p4. So my entire electron configuration for sulfur would be 1s2, 2s2, 2p6, 3s2, 3p4. And that should match up if you follow the configuration table correctly. Okay, and then also if you want to double check, just add up the number of electrons, and it should add up to the total number of electrons you have for sulfur. So if you look here, again, these exponents are the numbers of electrons in each sublevel. So sulfur has a total number of 16 electrons. So if I add up these exponents, right, 2 plus 2 is 4, 4 plus 6 is 10, 10 plus 2 is 12, and then 12 plus 4 is 16. That matches up with our total number of sulfur electrons. So again, you could do the same thing for lithium, right? Lithium has 3 total electrons. So you would just do 2 plus 1, that adds up to 3 total electrons. Okay, I'm gonna have you guys work on boron and phosphorus on your own, and then we'll come back together. Okay. So let's go over these examples. So boron, right, is right here. So if I just count from starting from hydrogen, so I have 1s1, 1s2, 2s2, and then here we're still on the second energy level. So this would be 2p1, not 3p1. Okay, so just follow the chart, 2p1. Okay, and then for phosphorus, kind of doing the same thing, right? So I have 1s1, 1s2, 2s2, 2p6, 3s2, and then for phosphorus, it would be 3p1, 3p2, 3p3. So that would be the electron configuration. Okay, now when we get to this sublevel here, it gets a little bit trickier. But as long as you follow the chart, you should be fine. So if you notice, right, after 3p sublevel, then we get to 4s, which is kind of like the same thing as always, right? But then if you notice right here, this D sublevel, it goes back to the third energy level. So this goes to 3D. And then when you pass the D sublevel, it'll jump up back to 4P. Okay, so why the heck does it go from 4S and then why does it go to 3D? Why doesn't it go to 4D like it normally should? So the reason for that is because these electron sublevels are written in terms of lowest to highest energy. So if you look here at this chart right here, we have energy going. So highest energy is at the top, lowest energy is at the bottom. And then if you look here, right, so energy level 1 only has one sublevel. So 1s is at the lowest energy. And then if you go to energy level 2, right, you have two different types of sublevels. You have the 2s sublevel, which is lower energy, and then the 2p sublevel, which is a little bit higher energy than that one. And then if you go to 3s, or the 3 sublevel, so you have 3s, right? That's the lowest energy, and then 3p is your next energy level. But then you actually also have a 3D sublevel. But the problem with that is the 3D sublevel is actually higher energy than the 4S sublevel. So if you look at this chart, right, it goes from 1S, 2S, 2P, 3S, 3P, and then 4S. So 4S is in energy level 4. And then it goes back to 3D because 3D technically has a higher energy than 4s does. So if you look at this chart right here, it'll go in the order of this electron configuration table. 1s, 2s, 2p, 3s, 3p, 4s, and then 3d. And then it'll go back to 4p. Okay, so if you're confused, just make sure you follow this chart and you don't accidentally write 4D here. You write 3D when you go in order. So if we go over these examples for the transition metals, so the D sublevels is always in the transition metal area. So titanium is right here, atomic number 22. So I would have 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, and then here I would have 3d1, 3d2. So not 4d, but 3d. So just follow it in order. Okay, same thing. We could do the same thing for gallium, which is atomic number 31. So I'm going to go a little bit faster, but we have 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, and then 3d. It fills all of the 3d sublevels. So I have 3d 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So 3d10. And then gallium would be 4p1. So that would be its electron configuration. Okay, and then lastly for this one, identify the element. Just kind of look at like the later, the last parts of the electron configuration, because the beginning is always going to be the same, right? So we have 4p6, 5s2, and then 4d2. So right here, 4d, and then it's the second element. So our mystery element would be Zr. Okay, so if you noticed, right, the S sublevels will always have 2 electrons per energy level. The P sublevels can have a max of 6 electrons. The D sublevel, if you count, right, 2, 4, 6, 8, 10, it can have a max of 10 electrons. And the F sublevel, we're not going to go over because either we're going to run out of time, but if we were in like not distance learning, we would go over these, but the F sublevels, they actually have 14 electrons. But you don't have to worry about them for this class or for online learning. So just worry up to the D electron configurations. Okay, why don't you guys do these next examples and then we'll basically finish up. Okay, let's finish this up. So for nickel, nickel is atomic number 28. So we're following the same idea. So I would have 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, and then I would have 3d, 1, 2, 3, 4, 5, 6, 7, 8. So 3d8. And then next element, bromine. So Br is right here, atomic number 35. So same idea. The beginning part, it's going to be the same. So 4s2, which is right here. And then all of the 3 sublevel is filled, so that would be 3d10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So 3d10. And then finally, we would have 4p, 1, 2, 3, 4, 5. So that would be bromine's electron configuration. And then the last part, again, I just kind of look at the last 3. So I have 5s2, 4d10. So 5s2, 4d10 would be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So it should be cadmium, Cd, would be my mystery element. Okay, so pretty straightforward. Just follow the chart and then you should be fine. Okay, let's go over the last or the main 2 exceptions to electron configuration. So there's 2 exceptions. It's chromium and copper, and technically anything that's in the same group as these elements. So like for silver, so EX silver, or you could also have, I don't know, MO, right? These would also count as exceptions to electron configuration. So the reason why there's an exception to these particular electron configurations is because of right here. These two these 2 ideas. So let me go over chromium and copper. So I'm going to write down the electron configuration for these 2 like they're supposed to be normally. So I would have 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, and then this would be 3d, 1, 2, 3, 4. Okay, and then same thing for copper over here. I would have 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, and this would be 3d9. Okay, so that's what it normally should be. But if you read here, it says a completely full D sublevel. So remember, D sublevels can have a max of 10 electrons. So a completely full D sublevel would be D to the 10. Or it says a half full D sublevel, which would be D to the 5. It says a completely full or half full D sublevel is more stable than a partially filled sublevel. So an electron from the 4s orbital is excited and rises to a 3d orbital. So what happens is these elements are so close to being either half filled or completely filled that what's actually going to happen is one of your s electrons is actually going to leave, and it's going to move over to the d sublevel so that it can become half filled for chromium, because the half filled or completely filled sublevel is more stable. Same thing with copper. What's going to happen is one of your s electrons will leave and move over to the deep sublevel. So it would go from 4s1 and then 3d10. Okay, so these are your two exceptions. Same thing for silver. Silver would also be an exception. So, right, if I write silver's electron configuration, it's kind of long, so bear with me. 3d10, 4p6, 5s2, 4d9. Same thing would happen, right? Your s electron, one of them will leave so that you could have a filled sublevel, 4d10. Okay, so these are your two exceptions, but basically everything else, you can just follow the order of the electron configuration table and then you should be good. Okay, yeah, so that's pretty much it. If you have questions, you can stick around. Otherwise, you guys are good to go. Bye, everyone.